And at some point, they might interact with some photons which are produced by my heavy nucleus. So from the point of view of perturbation theory of QED, an heavy nucleus is just a source of photons. It provides me a location of space-time, a pattern at which photons can be produced with some amplitude. So at the level of the action, for example, you have your path integral with some action of your fields. And then you'll add some sources. Say, I want to add a source at the origin that survives at all time. I will do something like this. I add some linear terms to my action involving the elementary fields times the sources. And this will create particles in my scattering amplitudes. Now, sometimes the consistency of the whole structure will impose some constraints on the sources. For example, we know that if we add something like this in electromagnetism, so if we add a source for the photons, this source better be conserved. Otherwise, it will source some of the ghosts, some of the longitudinal states which are not physical. This means that, for example, my nucleus I cannot introduce a nucleus which at some point in time decides to switch its charge without emitting any electrons. If I study the theory of gravity, the constraints might even be more severe. In the theory of gravity, the sources essentially have to propagate. It has to be dynamical objects which propagate properly in space-time, because the stress tensor will have to be conserved. And if I move away from the approximation in which my sources are infinitely heavy, maybe I have to include things like a recoil of the source or some higher order effects in which I have to allow my source to be modified at some higher order in perturbation theory. But as a starting point at the tree level, in a sense, just placing a source is a reasonable thing to do. Now, from the point of view of string theory, if I want a source for closed strings is simply something which allows strings to appear somewhere in space-time. So if I want to add sources to the string theory, I might have to study some scattering amplitudes, where some strings come and go. And perhaps interact with some other strings which are created at some finite distance. So, and these things are things that are supposed to go at infinity. These are particles coming in or out. But this is something that is really happening at some place in space-time. So the diagram is something like this. Represents something like this, where I'm just not drawing my source. Of course, no, this object can have, as usual, could have some handles, represent some loop process. Okay. So if I want to add sources to my string theory, I need to compute amplitudes where I include a certain number of these stubs. Location in the worksheet, or the worksheet just ends. It is the same way of saying boundaries. I need to allow worksheets with boundaries. So my string theory amplitude will be now a sum over the number of handles. Say this has one handle. And the sum of the number of and the sum of a number of boundaries. Then, so what does it mean to have a boundary? It means that the fields that live on my worksheet will have some boundary condition. Okay? So to make sense of this calculation, I need to give you a theory that lives on the worksheet. And a collection of boundary conditions. If I let your worksheet end, I better tell you how does it end. What are the rules for the worksheet to end? Mm-hmm.
So the introduction of boundary terms in, for example, in the worksheet, won't like violate conformal invariance or some other symmetries?
Well, so I wanted our theory to be while invariant and diffeomorphism invariant. And we require the same thing of our boundary conditions. I will elaborate more momentarily. So for each boundary, I had to pick one of my boundary conditions. So if you give me a collection of 5 boundary conditions, here I have 5 different choices I can do. Like, give me a list of 5 different nuclei that were floating around in space-time. Here, at the end of this photon, I can pick any of the 5 nuclei that you told me to put there. Mm-hmm.
What do these boundary terms mean at like the level of the classical action?
I will explain what the boundary condition is momentarily. For now, it's just a prescription of how to end space, the worksheet. The boundary condition just is a way you end, a prescription to make a boundary. Just like a theory is a recipe to compute correlation functions, a boundary condition is a recipe to compute correlation functions in the presence of a boundary. So once I've decided how many handles I have, how many boundaries I have, which types of boundaries, then I can do my usual two-dimensional field theory calculation. With these sorts of boundary conditions. And perhaps the vertex operators, which correspond to whatever particles I'm sending in and out. Then I need to pick a power of the coupling to be here. Usually the power of the coupling has to do with the integral of the curvature over my worksheet. And it just happens if I integrate over the worksheet like that, I get something like this. But actually, so here it looks like somehow I picked a very specific way to weigh the handles and weigh the holes. You may ask, why don't I do something else? Okay, why don't I do something else with the power of the boundary? But actually, I can. If you take this, just take this formula and take your collection of boundaries to include several copies of the same boundary condition. So suppose that your collection D consists of one copies of some boundary condition 1 and 2 copies of B2. anytime I have a boundary and I decide to put a V1 there, I can do it in any one ways. So effectively, my amplitude is multiplied by V1. But if I decide to put a V2 here, I get factor of N2. If I do a choice like that, I can apply the amplitude to the sum over poles and sum over the number of boundaries of type A, type A. Okay? And then I get 2G to the 2 and then G and A to the A. That's my amplitude. Okay. So, for reasons which will become clear momentarily, essentially, from the point of view of the field theory of closed strings propagating around, all that I did is to put some sources, and so for some bizarre reason, I want my source to be an integral multiple of this coupling. Now, why do I do that? Well, let's look at some examples first. Examples of processes. For example, suppose I have some closed string that scatters from a data. So scatters from a source. So some closed string comes in.
Could you turn the microphone on, please?
It is on. Now it's off, and now it's not on anymore. Buttons. Where the guy is?
No. Crawling his way.
Don't worry about it. I'll use a reminder.
Okay. God has spoken.
Okay. Is the tone of voice, the volume of voice sufficient for the remote? Anyway. So, suppose I want to study some process like that. There's an institute object which is creating these closed things. Now, I need to consider, as usual, all possible intrinsic geometries to the raw sheet. So I can look at this raw sheet and put whatever metric I want to it, and perhaps do some wire transformations. And although there are surely some metrics in which this is a very long cube that interacts with these other infinite cubes, there will also be metrics where this is very short. Perhaps there will be metrics where this actually looks like this. Now, calling it is going to be charge. I don't know if this is recognizable, but it's supposed to represent the cube with a hole. So that essentially for a while you're propagating a string, a ribbon, instead of propagating a cube. Perhaps I can make another example which might be too big. more striking. Suppose I interact twice with my source. This picture is topologically equivalent to this picture. And now again, they should have following lessons. So let me, this is Q, rainbow, Q. This is Q. These are photons. This is again a Q. Are these pictures at all recognizable? Okay, so it seems that at least in some corners of my parameter space of matrix, what the physical process looks like is very different from this. This here looks like a closed string is coming up, it's coming in. The hole is opening up, so it becomes an open. That's an open string. And then it closes again the closed string and keeps propagating to infinity. And here perhaps a closed string is coming in, it splits into two open strings, which make a loop, and then join again into the closed string. Now, this is rather interesting because it clearly works like quantum field theory. Whenever something propagates in an intermediate state, it actually has to be a state of the theory. Whatever can propagate for sufficient long distances is essentially a scattering state. So you discover two things. First, probably discover that probably our scattering things, the things that we can actually throw in and throw out, will include both closed strings, but perhaps also open strings. I can just cut this diagram here with some unitarity cut. And then I get a closed string coming in, two open strings going out. But also, you start understanding why perhaps these numbers have to be integrals. See, if I have really some open string states, then there will be some sort of a Hilbert space of open string states. Okay? So when I have a loop, for example, I'll be summing over a space of open strings. So the dimension of this open space of open strings better be an integral. So because I can interpret this sort of diagram as this sort of diagram. So here, as I said, N, A, and 1, G was just the strength of the source. But here, N1 is really counting the number of different objects which can go through, which I can transform into. And same here, I had an N1 and N2. And here it was just contributing to the strength of this source. But here, if you look at the combinatorics, that's telling me the product N1 and 2. It's sort of telling me the dimensionality of the space of states which are going for propagating this loop. So this is the reason for which the sources are quantized. You want the sources to be quantized in order for this picture to still make sense as quantum secure pictures.
Sorry, so are we claiming that you can have asymptotic on-shell states that are open strings coming and scattering and going to twos?
That's right. So let me step back for a moment. So when we were studying closed strings, we had diagrams like this. And the same string diagram have a multiplicity of quantum field theory diagrams corresponding to it. S channel, P channel, U channel. And when you compute the string amplitude, this will get singularities which correspond to all of these channels. And if you sort of impose unitarity of these singularities, will really tell you that you have processes like this, or processes like that. So essentially, these things on the right-hand side were set the list of all possible shapes you can get by pulling this string diagram around to make it look like a quantum field theory diagram. So if I apply the same strategy, I start from this and I start pulling terminal ways, I find the expected ones, but I also find a new unexpected one. But this one becomes something else, and then becomes a closed string again. Here, I find that if I pull the worksheet in some way, they start looking like this quantum field theory diagram. And when I say looking like, I really mean that when you compute something, you're going to find singularities which mimic the singularities of this quantum field theory diagram. So here you're going to find 1 over some, you're going to say some propagator with some mass or some state. And here you're going to find something that takes the looking data. But, so if you want, then if you want this theory to really make sense as a quantum theory, relatively, so it means that when you cut these things apart, that you can really write this object as the product of something times something integrated over intermediate states, or summed over intermediate states. And this sum is really a sum over states in a Hilbert space. So it involves adding up things which are counting, taking traces of some space. So you get integer things. So if your sources are multiples of integers, it turns out, I'm not proving it to you, but I'm just telling you that it turns out that this makes sense. So you can actually reinterpret it as some process which involves an integer number of intermediate states. If you put generic sources, which are not integer multiples of this, the combinatorics don't work out.
So are you saying that the intermediate states that I can have, are they the same ones that could live on my tube, or are you saying it's some subset of...
There's something else, something new, completely new.
Because we have
There's something we not put in.
boundary conditions, is that why it's a new thing, or...?
Right, so they correspond to open strings. They correspond to
Some...
not a loop propagating in spacetime, but a segment propagating in spacetime. And the properties of this segment depend on what you do at the x endpoints.
Okay, so when you say you can use unitarity to cut, and then that means I should be able to have a tube at least going into an open string. I should be able to put them together somehow smoothly. So.
That's right, that's right. So this is it. Sorry, Mike. Just take your tube and come out.
Okay.
This. Then the boundary conditions, you can carve out things. And this is your smooth join. So if you look at the combinatorics, these are the things that you might discover. So you find that there will be new open string states. So if you take an open string with boundary conditions BA and B1 and B2 on the two ends, propagating in space-time, you'll find N1 and 2 copies of some space of open strings. Simply because when you look at any picture like that, you always have in one different choices of copies of this boundary condition and 2 copies of this boundary condition. So then you diagram like this, you get a sort of combinatorial pattern like that in 1 and 2. And very roughly, the effective action for this theory, the coupling for this theory worked out as you had a coupling for the closed strings, which goes like 1 over G squared. And the coupling for the open strings, which goes like 1 over G. So let me just give a couple of examples.
How do the boundary conditions work out when you just have the single string state, the single open state?
So it means that so there are n1 and 2 possible spaces, n1 squared states of possible states of open strings, but only n1 of them can actually transform into a closed string. So a good way to think about it is sort of think about what non-abelian, well, the combinatorics of. So a good way to think about it is to think about open string states as matrices. So this open string state has, sort of carries some indices. It tells you which copy of the boundary you pick here, which copy of the boundary you pick here. So both these ones go from 1 to n1. But when you have this sort of process where you close your string, open string to a closed string, this choice must be the same as this choice. So this coupling will look like base of your open field, and like your closed field times by II of the open field. On the other hand, some vertex like this will have some by closed times some by ij open by ji open. Because here is some choice of my boundary conditions, here another choice of boundary condition, and this must be the same as this, and this must be the same as that. So just by looking at pictures, just by looking typically at a lot of pictures or worksheets and trying to interpret them as quantum picture concepts, you can discover this very basic fact about branes. When there are branes with those strings, you add sources to those strings, but you also create new degrees of freedom. The new degrees of freedom behave like a matrix. And couple both to each other into closed strings. I want to spend some time to make sure that the powers of the coupling that will be scattering around in scattering amplitudes do not look like complete mystery. So, what's a quantum field theory? When I write the action with just a coupling in front of everything. Okay? It's pretty much like okay. So here it has some propagator perhaps. and then some interactions. Okay. So that means that my interaction vertices would carry factors of G, 1 of G squared, sorry. And my propagators would carry factors of G squared. So let's start to doing some scaffolding. For example, if I have a process like that, what happens? I get 1 over G squared, 1 over G squared, G squared. Okay, that's the whole 1 over G squared. You can convince yourself that every time I have a 3-level process, I always have one more interaction than edges. So the whole factor is always going to be 1 over G squared. On the other hand, if I have some loops, then it matches different. If I have one loop, I have exactly the same number of vertices and propagators. So this gives me order 1. So in general, whenever I have some action that looks like this, the whole factor is G to the twice the loops minus 2. Now, under entertaining sort of combinatories, up here I have fields that are matrices. So suppose that some of my fields are matrices. Okay? So I have some normal fields and some other field which is really a matrix. Some Mij, where I and J runs from 1 to n. So, let me ignore the scalar for now. So, if we're going to draw matrix file fields, is a double line notation. So each line represents one of the indices. And we have interactions. So interactions always take the form of interaction is something like 1 over G squared trace of that. So trace dn plus n cubed plus the dots. Then your indices are always contracted across your interaction. Now, the process will start looking like that. And sometimes when you have loops, you're going to get extra combinatorial factors because you're doing a complete trace of 1. So here, for example, you're going to get it's a 1 loop, so no powers of G, but you're going to factor of n. So now the number of those group of indices is not always the same number of the actual loops you look at. So you can draw things that are not particularly very different. something like that, where number of loops, I think, is actually 4. Not this count. So I have 1 over g squared to the 1, 2, 3, 4. I have 1, 2, 3, 4, 5, 6 propagator. Okay. But I only have 1 closed loop of indices. I said 6, and then just square to the 6. So the number of loops and number of combinatorial factors are actually different. But a good way to visualize them is that you can imagine taking every closed loop of indices and sort of filling it in. So that this now looks like a surface with holes. So usually there's no canonical way to promote something when it makes lines to the surface. But you could blow up every line of the cube. But when you have this sort of indices going on, there is a canonical way to promote each line to a ribbon. But that's the best way to say it. So promote each line to a ribbon, each double line to a ribbon. Then this looks like a surface. And the combinatorial factors are g to the what put one of g. There's g to the 2 minus 2 twice the handles minus 2, and to the number of bundles. So this is one example which is complicated to visualize as a surface.
So what happens when you can't?
Let me make some simple example. So, let's start from here. So, and then G. And another false. So this, for example, in the middle of something that without external lines, which is be either. Let me just do the simplest thing. That. So I can interpret that as a sphere. When I just cut out the north pole and I cut out the south pole. So this looks like a sphere with 2 boundaries, which will also have out. So I expect to see something like g to the minus 2, and g and the number of holes. And indeed, this is a one-loop process. So I don't get any factors of g. And there are n square fields for getting out. So it's n squared. you can look at more complicated examples. But perhaps it's not the best use of our time. Actually, I didn't prepare enough examples in my head. So this sort of thing is very powerful in gauge theories, non-abelian gauge theory. In non-abelian gauge theories, your gauge fields are matrices, your quarks are matrices. No, dots are vectors, but gauge fields are matrices. So if you just look at the gauge fields, you get this sort of nice combinatorics. You look at the SUN in gauge theory, you get this nice organization of your loop diagrams by the number of boundaries in the genus. So this is called the Tooth expansion. And it's particularly useful to look at the theory which has a very large N. Because then sort of this term dominates on that. The most important diagrams are the ones where you have as many boundaries as possible. They're called planar diagrams. They're diagrams which are actually drawn on the plane as opposed to visual, which require an overlap. And sometimes you can say many more things about this properties of planar diagrams than about the properties of all planar diagrams.
For the formula to work for the non-planar one, I'm a bit confused. H would be 1 for that one, right?
Let's see. Yes. So
then it doesn't really work. So then it doesn't really work.
let me get rid of this so that it's easier to visualize.
Yeah.
Okay.
I mean, if you put in H equals 1, you get Gn to the V.
I think this is indeed talks with the whole.
I'm wondering if it should be G squared everywhere instead of G, because we get G squared N in the calculation.
No, I think it has to be G to get
Okay.
G and
But then it doesn't work because we get, you have calculated G squared and so.
well, sorry. Once I get rid of these guys outside, then there is an interpret.
Okay.
Yeah, sorry. I was getting my combinatorics not quite right because I was not accounting properly for the number of external states which are matrices. Sorry. So if you do something like that, it works. So the fact that you can sort of interpret the theory of processes which involve open strings and sort of large N combinatorics as processes involving closed strings and sources of order NG, which is called the Tooth coupling, is the basic reason behind something called Orota, the SMT. So in K theory, there is sort of equivalence between this current system in terms of sources which really change the ground, change your gravitational fields, or loops of open strings added to the theory. And the way the right way to think about it is that so sources are tricky, especially in terms of gravity. It's very hard to put a source, a light source, like that. Somehow, string theory deals with some of the singularities produced by these sources by transforming these singularities and interpreting them as something that results from the propagation of some open strings. So, or vice versa, it produces those sources to the formations of the closed string theory by loops of open strings. And in so doing, it regularizes them and allows for the theory to remain finite and well-defined. So the fact that you can mimic a gravitational background through loops of some matrix value fields is very important. It's actually arguably even more important than theory itself. Something was born from theory and then took a life of his own. It's called Volta theory, the SCFT. And I think it's going to be the subject of your next set of lectures. But it really has its origin inside its pictures. So this picture tells you that in some favorable cases, you have a quantum field theory of matrices, and you look at, you organize it by the number of handles and number of loops. Sometimes you can reinterpret it as processing some theory of gravity with sources of this magnitude and a coupling. This. So this is the essence of the SCFT. That there's somehow a gauge theory, a theory of matrices, a quantum theory of matrices, might be in some circumstances equivalent to a theory of gravity. Now you could arguably complain that here, it says, here in this complex string theory, in order to describe these sources, I added open strings, but I still had my closed strings. That's fine. So I had a space-time, a big space-time that I want to modify here in some region. And this modification is implemented by adding some open strings.
So are we claiming that the combinatorics are the same between the two? Or are we saying, like, even if you, because we showed, like, you know, compare the combinatorics of matrix fields and combinatorics of my strings, they look similar. But what about everything else? I mean, we're still doing the amplitudes. How do we know that those things are the same between the two?
So the combinatorics are the same.
Okay.
Now, there is something which is additional to that, but indeed I cannot show you here, is that there are special, as I'm saying, in string theory, what the deep brain does is it modifies it adds sources somewhere in your space-time, modifies your grounder by the means of adding closed strings, open strings to your system in that region. What's interesting is that in some situations you can then take something that's called a scaling limit, where you throw away all the rest of space-time and only focus on that new region. So you completely throw away the closed strings on this side. You're only left with open strings. And they're still able to encode the gravitational theory in that region, nearby region, near the deep brain. This is called open closed block. The fact that sources to closed strings can be mimicked by or regularized by adding open strings to it here. And I mean, this open string definitely has some bizarre properties. I mean, if you just were studying a theory of gravity, nobody had told you about string theory, it would be hard to figure out why to regularize some source, some black hole or something like that. I would have to add matrix values degrees of freedom to that object. But somehow this is produced by the combinatorics of the worksheet. Now, see. So tomorrow we'll start taking some testing results for our favorite theory of scalar fields, go through the details, and so on and so forth. Perhaps I can use the last minute to elaborate on something I wrote on the board there. So I said we needed a theory which is invariant under diffeomorphisms of wire transformations, and in some boundaries which are invariant under diffeomorphisms and wire transformations. So what does that mean? Well, so usually we very late. So if you study a space-time, a space without boundaries, right? There's some patch, there's some coordinates, then you will define your coordinates by some form of physics. Just the coordinate transformation. Typically, here with the boundary, and you want to study the diffeomorphism and parameterization of your coordinates, what you can require is that this theory is invariant and parameterization of the coordinates which do not move the boundary. So it pretty much means that you want your vector field to be parallel to the boundary. So if you define the normal component, the normal vector to the boundary, your diffeomorphism should satisfy A and A equal to 0 at the boundary. So a good boundary condition would be first of all a boundary condition which is well behaved under the circumstances. It's from physics. Now, usually we associate diffeomorphism invariant to conservation of the stress tensor. Then we say, take my metric, I change it by diffeomorphism, and that changes my action by something like that. And then usually I would say I integrate it by parts. Here is my conservation. Where this to be 0 means set this to 0. But if I have a boundary condition integrating by part, it becomes a little bit more subtle. I get an extra boundary term. So if I want material to be will be hard behaved under the diffeomorphisms, I will need to impose this to 0, but also this. So the component, I take my stress tensor, I look at the components which have one index perpendicular to the boundary, and one parallel to the boundary, that has to vanish. Now, this is actually not as strange as it sounds. If something happens for any sort of conservation law, for example, if we study a theory which has a U1 symmetry, so has some conserved current, and you want the U1 symmetry to be preserved by a boundary, you have the usual current conservation in the boundary. But you also have the statement that there is no current perpendicular to the boundary. This is saying there is no, the boundary cannot generate charge out of nowhere. This pretty much is telling you that the boundary cannot create energy out of nowhere. Now, so these are pretty much the conditions you need for boundaries to make sense in this story. And we'll look for this sort of boundary condition for this given all the time. And once you have these, pretty much you have all that you need to gauge fix diffeomorphism invariance and just go on with all the usual machinery. So you introduce your C's. Your C's will have the same boundary conditions as your vector fields. Introduce these. which would have the same boundary condition that your that tensor. And just keep going. There is nothing very new required to study the open space. The only thing that you require is to understand boundary conditions for two-dimensional problems. Okay. Any questions? I mean, maybe it's a bit big. It's a little wild. I would like to give at least some hint of how superplanes look like by the end of the week. We'll try to do it.